In the last video, we discussed how calculating the work done by a constant force was actually done using dot product. The dot product being a way you can multiply two vectors together to get a scalar. Um, Today, we're going to get back to our discussion of work and how we deal with that. But first, we're going to actually introduce a new type of force. We've discussed this before. We've mentioned it as the force due to springs and such. But today we're actually going to get quantitative with how to deal with that force. And it turns out there's a lot of situations where this type of force is essentially how we can model what's going on. From the way atom molecules move vibrationally in that to diving boards, trampolines, basically anything that has some sort of equilibrium position or a place that it wants to be. And if you push that system, whether it be a diving board and you bend it down, a spring and you stretch it, that system wants to go back towards that equilibrium position. It wants to go back to its sort of um, the state that it's comfortable in, we'll call it. But that equilibrium position, and it exerts a restoring force on whatever's trying to push it out of equilibrium. So in this case, you have a system and you displace it from its equilibrium and it pushes back trying to get back to that equilibrium position. Um, this These types of forces can be explained and modeled using what's known as Hooke's law. And um, so Hooke's law, the classic example and the one we're going to focus the most on in this course is springs. You have some spring that has some equilibrium length, L naught, we'll say. And so you attach a string to a wall and it sits there and relaxes at some uh, length L. If I stretch it some delta S to the right, that spring wants to pull back so we can get back to that delta L position. If I compress it and make it shorter, it's going to push the opposite direction uh, and try to again push back to equilibrium. And it turns out this can all be modeled again using Hooke's law, which is just the force, the magnitude of the force on that spring, or sorry, the actual force on that spring is negative k times delta s, how large that displacement from its equilibrium is, right? K is what we refer to as the spring constant. This is essentially a measure of how stiff that spring is. So if you can imagine like the springs in your car's suspension, they're extremely stiff. They would have a very large spring constant. If you compress them just a small amount, they're still pushing back very hard. Whereas something like a slinky, a very soft sort of spring, if you stretch that, even if you stretch it a pretty far distance, it's not pulling back with a significant force. So that would have a small spring constant. Um, if you plot the force versus the displacement, as you stretch that spring further and further, the force gets larger and larger, and we actually get the slope of that force versus displacement plot is negative the spring constant, right? The negative sign here essentially just means that it's what makes it a restoring force, right? Our delta S is equal to S, the position or wherever the end of the spring is, minus S equilibrium. So if I pull it to the right, like we've done here and stretched it, S is going to be larger than S equilibrium. And that K, or the negative K, means the force is going to be back in the other direction. So it's pulling back towards equilibrium. If I compress it here, that S that I'm located at when I stretched it to there is less than S equilibrium. So this would be negative. So when I multiply it by the negative K, I get a positive force. And again, it pushes me back to equilibrium. But the major takeaway from this is we can, use this just like we've used any other force, but we know that the magnitude, or sorry, the force on a spring is negative k delta s. Uh, and we can now use this, add this to our toolkit to analyze forces um, and how they act on an object. A quick example to go through is one from the textbook. Essentially, we have a toy train that's moving at 5 centimeters per second to the right, attached to a 2 kilogram block that has some coefficient of friction between it and the surface, and some spring with some spring constant K. There's a coefficient of static friction there. And so this train, at t equals 0 starts to move. How long does it take? When does this block start to slip and follow it, right? We would analyze this the exact same way we've been analyzing forces before. So the first thing is pick the object we're going to describe. We're going to try to describe this block because it's whatchamacallit. It is, we're looking to see when it moves. We circle it, we identify all the forces. There's a frictional force, the static friction on the ground. There's a normal force. There's the force on the spring because the spring is touching it as well. And those are the only things touching it. So then those are the contact forces. And then there's a long range force of gravity. We can then build that and draw a free body diagram. Normal force is always going to be straight up. Force of gravity straight down towards the center of the earth. Force of static friction keeping it stationary, and the force of the spring trying to pull it to the right. Building off this, we essentially, our last part is F net equals ma. If we look in the y direction and analyze this, we have the normal force minus gravitational force, because those are the only forces in the y direction, is equal to 0 because it's not accelerating up or down. And we have the normal force is equal to mg. If we look in the x direction at the x components, we have the force due to the spring in the positive direction and minus the force of static friction in the negative direction. And since we're looking at when that object's going to start sliding, we're looking at trying to figure out the point where Fs is equal to Fs max, right? When those are equal, that's going to be the time that that block starts moving, because time's going to slowly increase. Fs is going to get bigger and bigger and bigger. It's going to reach Fs max. That's when it's going to slide, at that instant that it crosses that. But at the last instance it's stationary, it still hasn't accelerated. So we have the net force is going to be equal to 0. Now, the Fs max is just coefficient of static friction times the magnitude of the normal force. And the force on the spring is K times delta X. Now, this is going to be equal to 0. This is kind of a confusing part. In the last slide, we said the force of the spring is equal to negative K delta S or delta X, because we've labeled this in the X direction. What happened to this negative sign? Why is this force in the spring positive? And the answer is essentially you have to sort of think about what end of the spring you're on. So if this is the spring and the train's over here pulling it that way, and the blocks on this side, that spring, this delta S, has gotten larger. So the simplest way to think about it is it's trying to get shorter. So it's pulling this end that way and that end that way is the force that the spring's exerting. So if we're looking at the block, it's going to be pulling to the right. It's going to be positive. So one of the ways I recommend when you're first starting to think about forces on the spring is think about the magnitude of the force on the spring. And it's just going to be K times delta X. And then sort of think of what side of the spring, how is it pulling? Is it stretched and pulling me to the right? Is it compressed, pushing me to the left? But think about what end of the spring you're talking about, and get the direction from there and use that to get the sign. But anyway, so we have this situation, and we can use this to figure out what delta X is. So we know that that block will start to slide when the spring is stretched, or i.e. the train has moved, some delta X equal to mu S times the normal force over the spring constant K. When we already went through that, when we go through that whole calculation, we end up with this delta X is equal to 23.5 centimeters. Now I'm going really quickly through this. This is written out in the textbook and all that is example 9.8. So if you need to revisit it, you can go through there. The next question, though, is the question asks how long does it take for that block to slide? And to do that, we just look at, well, we know the speed that train is going. The velocity was 5 centimeters a second, and we know that that is the change in position over the change in time. So we can use this to solve for the time it takes for that block to start sliding is going to be delta x over the speed of that train, which ends up being 4.7 seconds when we plug in all those numbers. So nothing extremely new here other than we know how to calculate the force on the spring is equal to the magnitude of that force is k times delta x, how much that spring is stretched. What does this have to do with work? Well, I like this problem mostly because it highlights, it's kind of a, I think it's kind of a BS problem, right? For this train to be moving at a constant speed like this, it needs to have a constant force on it, right? It has, a net force of 0. So all of the forces acting on this train would have to be balanced, but we know the force due to the spring is changing. As it moves, the string is stretching more and more. So that force is going to be different. So that means the throttle or whatever's pushing the engine on this train would have to change its force in exactly the same way that way to keep this constant. So if you really think about how physically likely this sort of situation is, it's not really. This is kind of a made up problem that is only, kind of designed to say, oh, can we use that? But I don't think this is a really realistic problem. And the main reason for that is we're looking at a force that's going to change, right? All the stuff we've done in forces for the most part in dynamics have been constant forces and things that don't really change. And if we put in a non-constant force, if you think back to your lab with the parachute and that, it gets a lot harder to deal with using dynamics. Turns out, since we know the sort of functional form of this force, using work can make dealing with spring forces and that often much, much simpler for us. So to see that, recall how we first defined work. If you remember, we went through the derivation from Newton's second law, but work for any force was shown to be this: the integral of the force with respect to the displacement between the start and the end points, right? And then we said, well, if this force is constant, we can pull it out, and that work for a constant force was just that F dotted to delta S. That's what we talked about last time. This was for a constant force, and it was because we would be able to pull that force out of the integral. Well, now we're in a different situation where that force isn't constant, so we can't pull it out. But we can actually, since we know the force on a spring, how it relates to position, we can actually perform this integral. So to see what I mean, let's actually look at an example. Let's say we have that spring attached to a wall, and I've compressed the spring some initial amount, delta S initial, delta SI, in towards that spring. And we're curious of how much work is done as that spring moves to some other position. Well, in the last slide, we showed that work is equal to the integral from the initial position to the final position of that force with respect to that position, right? We know from Hooke's law that the force due to spring is just negative k delta, delta S. I'm just going to write S ds, and I'm going to call S equilibrium. We'll make that our origin 0. You don't have to. You can go through this all without that, but this kind of just makes the integral and everything easier. If I do that integral, the integral of S with respect to S ends up being S squared over 2. So this whole integral ends up being 1/2 negative k S squared, right? And if I evaluate that from those two limits, S final to S initial, what I end up with is 1/2 negative 1/2 k S final squared minus negative 1/2 k S initial squared. And if I, arrange, this negative and negative become positive, this one stays negative, I get 1/2 K S initial squared minus 1/2 K S final squared. Or written the way they do it in the book, this is negative 1/2 K S final squared minus 1/2 K S initial squared. Because we know the functional form of this force, we can actually do this integral quite easily. And then all we need to know is the initial and final positions of that spring that's been compressed that we know, and we can figure out the work done by that spring. If we know the work, we can then use our work kinetic energy theorem to figure out the change in kinetic energy. And this is a much more straightforward way than using, say, Newton's second law in dynamics with a varying force to try and figure out, a final speed or something. So, and this, so the work done by a spring that has been compressed and or stretched uh, is kind of a very useful tool to help us analyze problems that would be very difficult using straight just Newton's laws. And it all comes from the thing that sort of underlies why it's simpler is the fact that the force is varying. It's not a constant force. So using Newton's laws can kind of get really challenging because that's going to essentially lead to an acceleration that's not constant. So kinematics can be really hard to do. Um, anyway, we'll work through some examples in our synchronous sessions and on the homework and that, and hopefully it'll start to become clear why that's useful. For now, these are the big sort of things from this lecture. Hooke's law, the force due to on a spring or some object that has equilibrium and has been displaced by some delta x. The force due to, on that is negative k times delta x. And the work done by a spring is equal to negative 1/2 K delta X final minus 1/2 K delta X initial. So those are the major two takeaways, and we will do some more examples and work with those as we move forward in this. If you have any questions, email me or ask me in the synchronous sessions.